Alright, so we're in section 11.3. So what we're going to do today is talk about the slope of the graph of a function. So let's start off. We're going to look at this visually a little bit first, and then come up with some equations. So let's say we have some kind of function, looks like an upside down parabola maybe, and we want to talk about the tangent line to this curve. What do we mean by tangent? Touches it in one place. So if I look at the tangent line here, so I'm talking about this line here. If I talk about the tangent line here, I could have a tangent line like so. Thank you. And we're touching it right there, and so on. So tangent line, we're talking about this line that's touching the curve in just one point. Now, it's a little, we could have curves where the tangent line intersects the curve in more than one place. So if we had something that was like one of our trig functions, a sine or a cosine function. So if our curve looked like this, if we look at the tangent line here, let me draw that in red. We look at the tangent line here, it's going to intersect the curve in more than one place. But what we're interested in here is the place where it's just touching the curve like so. So even though it intersects, the tangent line intersects the curve down here, we're interested in this point. The tangent line tells us something about how quickly the function, whatever function this graph is describing, how quickly it's changing. So here we know that the function's increasing, it's going up, it's getting bigger. Here our tangent line, we know it's getting smaller. So our tangent line tells us something about how our function changes. For example, if this graph represented the position of a particle, say the y is our position and say x is time, the tangent line would be telling us about the velocity of the particle. And that's one of the big things that mathematicians have tried to do over the years is, if we know the relationship between two quantities, between x and y, when x changes, how does y change? That's one of the basic questions that we try to answer in math. So what we're going to be talking about, what we're interested in with these tangent lines, is their slope. And we're going to call the slope of the tangent line at this point, we're going to call that the slope of the graph at that point. So the slope of the tangent line is the slope of the graph at the tangent point. So we're interested in the slope just at this one particular point. And that's going to tell us how that function is changing at that one particular point. What we're going to do today is come up with a process for finding that slope. Because normally when we talk about slope, if we're talking about the slope of a line or slope between 2 points, we need 2 points. We need to figure out the rise, the run, that kind of thing. So we're going to do that exact same process, and that's where this idea of a limit is going to come in. So let me draw another picture of a graph and the slope of a line, and we'll talk about how this idea of a limit gets mixed up in here. Is everybody good at what we mean by the slope of the tangent line, the slope of the graph at a point? Okay. So here is another picture of another graph. make my line roll. Okay. So here are my axes, and I have this curve along here that's doing this. And let's say we're interested in the slope at this point, and we're going to say that is at position X. What we're going to do is approximate that slope by drawing in what we call a secant line. So we're going just to connect two curves, or 2 points on the curve, with a line. And we'll say the slope here is approximately the slope of this secant line. Secant line is a line that cuts through in 2 places. Secant means to cut. And what we're going to do is I'm going to bring this down here like so. And let's say we move a distance h. So this point is going to be x plus h. And my function value here is just going to be f of x, whatever the function is. And the function value here is f of x plus h. So the slope of this secant line is the rise. Well, the rise is f of x plus h minus f of x. So if we draw in this here, this distance is f of x plus h minus f of x. And the run is h. That's how far we've gone in the x direction. So there's the slope of this secant line. Now what we want to do is, now we're going to draw the same curve, and I want that distance h to get smaller. So here's my curve again, and I'm going to look at the point x. That's where we want to find our slope. And I'm going to put the secant line here. So I'm going to draw my secant line to find my slope between those 2 points. And that distance is still h, and this is still f of x, and this is still f of x plus h. And what we want to make that distance h smaller and smaller. So we want this distance to get smaller and smaller, so these 2 points to get closer and closer and closer together, so that the secant line gets closer and closer and closer to the tangent line. So what we're doing is we're taking the limit as h approaches 0. X plus h is getting really, really, really close to x. The secant line gets closer and closer and closer to the tangent line. And our slope of the tangent line is the limit as h approaches 0. These 2 points are getting closer and closer together, of f of x plus h minus f of x over h. So we're just taking the rise over the run, and we're letting the run get smaller and smaller and smaller and smaller.
Mr. Peter, can I interrupt you for 1 second?
Sure.
This is Marin.
All right. So we want this distance to get smaller and smaller, so our run gets smaller and smaller and smaller. So that's what this quantity is telling us. The slope of the tangent line is the rise over the run, as the run gets smaller and smaller and smaller and smaller. So this is going to be the slope of the tangent line as long as this limit exists. So let's do some practice. I want to do a couple of examples of calculating. We've seen this quantity before. We did some work with it here and there. We called this the difference quotient. So I want to do some examples calculating with this limit. So this is where the idea of a limit comes in to find the slope of this tangent line. All right. So let's do some calculation. We want the slope of the graph of y equals x squared plus 1 at the point 1, 2. So our slope is given by this limit. Limit as h approaches 0 of f of x plus h minus f of x. That's our rise over our run, h. In this problem, x equals 1. So x plus h is just going to be 1 plus h. So that's what I'm going to plug in here. This tells me to evaluate my function at x plus h. So I'm going to evaluate my function at 1 plus h. So we're looking at the limit as h approaches 0. This says plug in 1 plus h for x. So I get 1 plus h squared plus 1. That's what my function is. Minus f of x is f of 1. F of 1 is 1 squared plus 1. And we're dividing that by h. And now to evaluate this limit, we just need to simplify. So we're using the same rules that we used before. As h approaches 0, we want to simplify this quantity so we can evaluate this limit. All right, so let's expand this out. So when I square this quantity, I get h squared plus 2h plus 1. That's when I square this out. And I have a plus 1 and a minus 1 and a minus 1.
All kinds of good stuff going on. I just want.
All right, and then we're dividing this by h. Well, I have a plus 1, a plus 1, a minus 1, a minus 1. So those all go away. And I forgot to write my limit here, so I should write my limit. Limit as h approaches 0, and I'm going to factor out an h here. So I get an h times h plus 2 over h. All these 1s go away. The h's cancel. And I get the limit as h approaches 0 of h plus 2. And that limit is what? As h approaches 0? 2. So the slope of x squared plus 1, the graph of x squared plus 1 at the point 1, 2 is 2. I plugged in x plus h. Here x was 1, so x plus h is just 1 plus h. F of x is f of 1. Plug that all in and simplify. And that gives me the slope of that graph at that particular point. Questions about that process? So what usually confuses students is this idea of x plus h. That's just telling whatever x is, we're plugging that into our function. So I plug in x plus h for x and evaluate that function. That's what this quantity is. All right, so we can use this process to find an equation for the slope as well. So rather than finding the slope at a particular point, here at x equals 1, we're going to find the equation of the slope for any value of x. So we can use this limit to give us an equation for the slope. So let's take a look at an example of that. So we want the slope of, and we're going to graph f of x equals 2x squared minus 3. at any point x. So we want the equation of the slope of this graph at any value of x. So here the problem, we have the same thing. Our slope is going to be the limit as h approaches 0, f of x plus h minus f of x over h. Here x is just x. X plus h is just x plus h. So I'm plugging that into my function. So I'm going to say this is the limit as h approaches 0. F of x plus h is 2 times x plus h squared minus 3. I'm just plugging this in for x here. Minus f of x, that's just f of x. And we're dividing that by h. And now we're going to simplify this. So when I multiply this out, I get the limit as h approaches 0 of 2 times x squared plus 2xh plus h squared minus 3 minus, and f of x is, I should say f of x is 2x squared minus 3 here. That's f of x. And we're dividing that by h. So let's continue to simplify. The limit as h approaches 0, I get 2x squared plus 4xh plus 2h squared minus 3 minus 2x squared plus 3. And we're dividing that by h. Well, now I have a lot of things that cancel. So I get a 2x squared here, and I get a minus 2x squared there. I get a minus 3 and a plus 3. So this turns into the limit as h approaches 0. I'm going to factor an h out of this. So I get h times 4x plus 2h over h, and we're almost done. Those cancel, and I get the limit as h approaches 0 of 4x plus 2h, and that limit as h approaches 0 is what? 4x. So the slope of the graph of 2x squared minus 3 at any point is 4x. So I can plug in a value for x for any point, and I can find the slope of this graph at any point. So rather than finding it for one point and then having to find it again for another point, we go through this process, and that lets us figure out the slope at any point. Questions about our process there? All right. This idea of finding the slope of the tangent line at a particular point is so important that we give it a special name. That's people as far back as Archimedes, even further, have been trying to figure out this idea. How do we find the slope of the line at a particular point, the slope of a graph? How do we find how that function is changing at any particular point? So we call this limit the derivative. The limit as h approaches 0, we've written it a whole bunch of times now, f of x plus h minus f of x over h is the derivative of f of x. The derivative tells us the slope of the tangent line at any point. The slope of the tangent line, I want to write out a few other ways that we can refer to it. So the derivative gives us the slope of the tangent line. The slope of the tangent line, the other ways that we can refer to it, the rate of change of f of x with respect to x. So the rate of change, the derivative gives us the rate of change. So if our function is describing a position, the derivative would tell us the velocity. How the position is changing with time. The other way you'll hear the derivative referred to is the instantaneous rate of change. So it's giving us the slope of the tangent line at one point on the graph. That instantaneous rate of change. It's not an average rate of change. It's not between 2 points. It's at exactly 1 point. Instantaneous rate of change. The other ways you'll see this written, so this limit is our definition of the derivative. The derivative is a limit. The other way that you'll see it written, dy dx. You'll also see it written as d dx. D means derivative or rate of change. The rate of change of y with respect to x. Derivative of y with respect to x. Derivative with respect to x of f of x. Or you might also see d sub x as a subscript. And sometimes you'll see d sub x of f of x. All of these things mean exactly the same thing. All of these refer to the derivative, and the derivative refers to this limit. We're finding the slope as the run, the change in x gets really, 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 really small. All right, questions on what we're talking about when we're talking about the derivative. So next year when the derivative is one of the two main ideas that you'll learn about in calculus next year. You have the derivative and you have the integral. The derivative is the first thing that you learn about, one of the first things you learn about, because we've talked about limits, you'll talk about limits a little more, and then you will learn about the derivative and how to find the derivative of all kinds of different functions. Because the derivative is one of those ideas in math that's so fundamental, so important, that from here on out, kind of like limits, everything that you do will involve derivatives. Once you learn how to use the derivative, it's like, I wish I could have learned this back in elementary school, because it makes problems, lots of kinds of problems, way easier than the way we've had to do them before. So we had to have the knowledge, the sophistication to use this idea of a limit to come up with our derivative. All right, so let's look at one more example of finding a derivative. And then our homework tonight is just practicing using this limit. So let's find the derivative of f of x equals 1 over x. And the other thing that you'll do in calculus is for some functions, you can generalize the process. So there's kind of a shortcut, or shortcuts that you can use. For now, we're just going to talk about the limit, or the limit definition of our derivative. So our derivative, we're looking at our limit as h approaches 0, f of x plus h minus f of x over h. So here, for this example, we're looking at f of x plus h is 1 over x plus h. And minus f of x. F of x is 1 over x. And we're dividing that by h. What do we need to do here to simplify our limit, to be able to evaluate this limit? We did a problem like this in our homework a couple of days ago. What do we have to do up here in the numerator? Find whole numbers. So what's the other way we say that? We want to add these fractions. Subtract these fractions. How do I subtract these fractions? We need a common denominator. What's our common denominator for x plus h and x? X times x plus h. So I'm going to multiply this fraction times x plus h over x plus h. And then multiply this fraction by x over x. So now I can add those fractions. So I get the limit as h approaches 0. And when I add these, I get x minus 1 times x plus h over, and my common denominator is x times x plus h, and I'm dividing by h, so I can write that h right there. Dividing a fraction by a number, I can put that number in the denominator. Well, this simplifies. This turns out nice. This is the limit as h approaches 0. X minus x is 0, and I get minus h over h times x plus h. And my h's cancel. And I get the limit as h approaches 0. I have a negative 1 left in the numerator, and an x times x plus h. And as h approaches 0, what is this limit? Minus 1 over x squared. So the derivative of f of x equals 1 over x is minus 1 over x squared. This would give me the slope of the tangent line to the graph of 1 over x at any point. So you can sometimes people kind of say half jokingly that part of calculus, part of the idea of calculus is giving us a trick to be able to divide by 0. So here we're letting our h go to 0. This limit process gives us a way to essentially divide by 0. Not really divide by 0, but kind of get around that thing where we're having to divide by 0. So this gives us the slope of our tangent line to 1 over x at any particular point. Questions on the process we use there? So once we do our substitution here, now we're just back to evaluating limits using the rules that we used for evaluating limits that we learned back in section 2. And the homework tonight is all working with the idea of using this limit. For the homework, remember that point-slope form. What's point-slope form for a line? Y minus, get a start of y minus y1 equals m x minus x1. So there's a problem or two in your homework that will say find the equation of the tangent line at a particular point. Well, your point is y1, x1, y1. The derivative, that limit, gives you the slope, so you can find the equation of the tangent line. What's the slope of a horizontal line? 0. What about a vertical line? What's the slope of a vertical line? Undefined. So there's a problem that says find all the points where the tangent line is horizontal. You're looking for where the slope is 0. I don't think any ask you for the vertical tangent line, but that would be where the slope would be undefined. All right. And don't forget our other techniques that we've used for simplifying limits. You might have to multiply by a conjugate to simplify a limit that has to do with radicals. You might have to do that in your homework. So don't forget those other things that we've learned. All right, there we go. And